others will join later. So number 6, the class of polymers called polycarbonates are made by the reaction of carbonyl dichloride with a diol. Okay, so you are going to get a polycarbonate and you are going to get HCl. Okay, so when I look at this, I see there is going to be 2 OH groups. Okay, so I have R, another OH. So if I have C double bond OCl, Cl, okay, I can see that maybe this one, okay, they will come out, and then this one with another diol, and this one, okay, with another this molecule. So they are going to give you this polycarbonate. So we are removing certain things. Therefore, the type of polymerization here is going to be condensation polymerization. In our syllabus, we have 2 types of polymerization: addition polymerization and condensation polymerization. So addition polymerization we see when we have unsaturated hydrocarbon. So whenever they have double bonds, okay, then we can actually have addition polymerization. In this case, it's a condensation polymerization. So Nalgene is a polycarbonate formed from diol P and COCl2. So something similar. Okay, so if I have C double bond OCl, Cl, okay, and what will happen? Okay, let's say I just put another one molecule over here. So similar reaction will happen. Okay, the H will go out with the Cl, and this H will go out with this Cl. So what we are going to have, okay, similar, this one will also go out, this one will also go out, but they want one repeating unit, not the entire polymer. So how do I draw? Okay, so this one I'll just redraw again. So CH3, CH3, O. Now this O will be connected to C double bond O. Then this is going to be, there is one part. Okay, so here at this side, they supposed to have O connected also with C double bond O, then another part. But okay, when you want to draw one repeat unit, okay, better to look at this structure here. This is one repeat unit. You see carbon double bond O, okay, and another O. So this was something like similar to that. And it ended from R with O. So ended over here. So to show one repeat unit, you do not need to show this part. Okay, you do not need to show this part. So I'll just put, you just need to show up to here. Up to here. So if I want to, better way is to remove this. This is going to be one repeat unit. Okay, one repeat unit. Now, Nalgene is a strong and tough polymer. Identify 2 types of intermolecular forces that are responsible for these properties of Nalgene. So intermolecular forces, you see we have hydrogen bonding, we have van der Waals forces of attraction, we have permanent dipole-dipole bonding. Okay, there are 3. So if you look over here, the one that I need to include here, I can see straight away, okay, there is no hydrogen bonding. Why? Hydrogen bonding must have a hydrogen bonding with NOF. Okay, so I don't see that. Okay, there's only oxygen here. So here, I will ignore this part. So I will have van der Waals forces of attraction. Okay, so just put van der Waals forces, and we can also have, okay, the permanent dipole-dipole forces of attraction. So van der Waals forces in your in your marking key, they give it ID forces, induced dipole, or London forces. Okay, but all these are van der Waals forces of attraction. Okay, so this one is going to be, you can actually write down van der Waals forces, no problem. And here is going to be permanent dipole forces. But again, if you want to be safe, okay, so instead of writing van der Waals forces, you still want to actually be safe, then induced dipole, induced ID forces, ID. It's supposed to be temporary dipole, induced dipole. Okay, but it's okay, we'll just follow ID forces. Okay, you can still give it as van der Waals forces. Okay, still okay. Now, proteins are polymers of amino acids, and complete the table to show how the secondary and tertiary structures of proteins are stabilized. So secondary structure, okay, you need to know secondary structure is stabilized by hydrogen bonding. The groups that are involved, okay, is going to be the carbon double bond O and nitrogen and hydrogen. These are the groups, okay, that are going to be involved. It means it's the forces between the C double bond O and the NH. Okay, so it's actually between these two. So this will stabilize the protein structure. And for tertiary structure, okay, we have many. To be exact, 4. Okay, so I wrote everything here. For tertiary structure, we have disulfide bridge. Okay, sulfur and sulfur between the R groups. Van der Waals forces between the non-polar and non-polar R groups. Hydrogen bonding if you have polar side chain and the NOF residue. Ionic bond, okay, if we have ionized acid with ionized basic side chain. So you need to choose one, okay, just choose any one of these. So if I want to choose, let's say I choose hydrogen bonding, okay, then you need to mention properly. So let's say now I put disulfide bridge, okay, disulfide bridge, but they say intermolecular forces, yeah. So I think the disulfide bridge also, even though it's intermolecular forces, maybe I'm not sure whether they are going to be there in the marking key. For example, if you have that confusion, then be just select either this or this. If you have doubts, okay, if you have doubts. So let's say I'm just going to select van der Waals forces. Okay, so I'll just put van der Waals forces. So van der Waals forces, the group involved is going to be the non-polar and non-polar R groups. Okay, this is going to actually create the van der Waals forces of attraction, but there are total 4. Okay, you can choose any. Next, explain the significance of hydrogen bonding in DNA. So this one you see, for this kind of questions about protein, you can see maximum. Okay, there is going to be 2 marks plus another 2 marks. So please take note. They will not ask too much of question over here, but you need to be able to explain. Okay, so here they say related to hydrogen bonding. Explain about significance in DNA in relation to accurate replication of genetic information. So in accurate replication of genetic information, it is, you need to mention there is going to be hydrogen bonding between what? Okay, the hydrogen bonding is between the base pair. Okay, the base pair, okay, they are called complementary base pair. So you can say hydrogen bonding between the complementary base pair. That's going to give you 1 mark. So you need to tell what are the base pair that is going to complement to each other. So A to T, you can just use the A to T, and then C to G. And if you want to mention about the number of hydrogen bonding that will be there also I have written, but no marks given here. Okay, but if you want to mention, you can mention that there are total 2 hydrogen bondings that can exist for the bonding between A to T. And there are 3 hydrogen bonding that can exist between C and G. Okay, this complementary base pair. So what are the marks? Okay, the marks are given for hydrogen bonding between the base pair. And if you mention A to T and then C to G, then you will get another 1 more mark. So complete 2 marks. Now, many polymers are degradable. Okay, this one I told you to read about it. Okay, because the biodegradable. Okay, whether certain polymers, whether they are biodegradable or not, it depends on the structure. Like for example, if you have nylon, nylon is going to be a polyamide. So nylon and polyester, okay, you can read from the textbook, they mentioned that acid hydrolysis can be used to break the bond. Basically like ester, if you have ester, you can break the bond, okay, between the ester. Like for example, if you have R and R, you can break this particular bond, okay, but you need hydrolysis reaction, okay, acid hydrolysis. So then the polymer can be broken. Another way is by using the sunlight. Okay, we call it as photodegradable. So this photodegradable is especially whenever you have polymer that has the carbonyl group. Okay, because most of the time the polymer will have this group, and this group, whenever you have C double bond O, whenever there is UV light, okay, this UV light will make that bond between C double bond and O to become weaker, and they are going to break, and this will make them to be biodegradable. So what are the state 2 different process which some polymers can be degraded? One, you just say hydrolysis, no need to be specific because there is also basic hydrolysis. Okay, we have acidic hydrolysis, so hydrolysis will do. The second one is going to be, because it's going to be photodegradable, you can say better way to say photodegradable by using sunlight. So you say by using sunlight or UV light. Now, next is going to be a cyclic peptide B is shown. Okay. Now, for this one, maybe I have written over here. So maybe I'll use a different ink over here so that you can see. So what I did, okay, maybe I think better I'll just do it again. What you can see over here is, okay, you are going to have this molecule. And when I have cyclic peptide B is broken to its monomer by heating under reflux with dilute hydrochloric acid. So the amino acid, okay, and 2 other products are formed. So you have one of the amino acid here. So I want to know what are the others, okay, but you see this is going to be breaking the bond, okay. It's a hydrolysis. So the bond that will be broken is going to be the bond between carbon double bond O and an H. This particular bond will be broken. Okay, the peptide bond will be broken. So we need to break. So I'll just put it here. This bond is going to be broken. This bond is going to be broken. So I'll write down first. Sorry. Okay, I've highlighted which are the bond that will be broken. And when that bond is broken, okay, I will write down, okay, what will be the possible structure that you are going to obtain. So for this one, you will get NH, okay, you will get another H. So this one is bonded to another carbon, and then you have another carbon, double bond O. So this part will be OH. Okay, you have this structure. And for this structure, this is NH2. So I put NH2 bonded to carbon, bonded to another carbon, bonded to benzene group, and then bonded. Okay, this carbon is also bonded to another carbon, C double bond O, and then this one will be OH. Okay, so I'll just put it as, okay, this one, and then you have this one for this. So here NH, so bonded to carbon, and then this carbon is bonded to carbon, bonded to another carbon, bonded to benzene, and then this carbon is bonded to another carbon, double bond O, and then OH. So this one belongs to this. NH2 bonded to this carbon, then another carbon, double bond O, OH. For this one, so I have C double bond O, OH, then bonded to another C, and this C bonded to NH2, and then this carbon is bonded to another carbon, and that carbon consists of OH and also CH3, another CH3. Okay, you can just put. Okay, two more. So NH2 bonded to this carbon, then you have another carbon, and then you have this, and the carbon here bonded to another carbon, double bond O and H2. It's going to be for this. Carbon, double bond O, OH, then another carbon, NH2, then one carbon, another. Okay, done. Now, if I put it down, they say that, okay, there is going to be threonine. Okay, threonine. Now, if you look at threonine, okay, this structure is the same as this structure. Okay, it's the same as this structure. And you are looking for two other groups. Okay, so here, when I see the groups, the one that I circle over here, I only see like if this is one, this is the same as this, and it is the same as this, it's the same as this. And if I give you number 2, this is going to be 2 is the same as this 2. Okay, you can see all of them are the same. Let me check, yeah. COOH, carbon, NH2. Okay, just double check, yeah. So what I will achieve here is I am going to have one structure, okay, that is going to be attached to the benzene. Another structure is without any benzene, which is going to be the structure. Let me check. Yeah, this one is C double bond C, CC, OH, and then CH3. And then this carbon is bonded to COOH and then NH2. So this structure, okay, it's not belong to this. I think this structure belongs to This is similar to number 2. This is similar to number 2. Okay, so here what I need to write is this C double bond O, OH, C double bond O, OH, C, and then NH2. This is what I need to write. And another one is this one. Okay, so C, C, COOH, NH2. Okay, you can write it like this. Okay, or okay, you want to give it in skeletal formula also can. Okay, but whatever it is, okay, make sure you write properly. Make sure all the carbon are all written properly with all the proper bonds and so on. Okay, you will get this too. Okay, so this one belongs to this one belongs to this. So identify first, and then using the 3-letter abbreviations, okay, given in the data booklet, complete the sequence. Now, this is, okay, threonine. Threonine, they put THR. So I found out, okay, that, okay, this molecule, the one that it has number 1 over here, okay, you can check in your data, you can check in your data booklet. Okay, you will see what you need to see is going to be how to see is, I think here, hold on, yes, C double bond O, and then this is OH. How to see is just look at this portion, this R group. Okay, you will notice that, okay, if the R group is like this, then they will say the abbreviation that we supposed to use is PHE. Okay, for this one, okay, if I have something like only H, okay, if the R group is only H, okay, the R group, this is going to be the structure. If your R group is only H, then they say this is going to be glycine. So you just need to put, okay, because I found out this is going to be 1, 1. So 1, 1, PHE. And then we found out this is going to be 2, which is similar to this. So this is gly. And then the rest are the same. Okay, PHE, PHE. And then you complete this one. This one you look at your data booklet. Now, name 2 analytical techniques that can be used to separate amino acids. Now, to separate amino acids, okay, you must use electrophoresis. Must, yeah. There is no. If you want to separate amino acids, you cannot ignore electrophoresis. Okay, electrophoresis. And okay, once you separate the amino acid, you can test. You can do further analysis using thin layer chromatography. Another way may be paper chromatography, but other than that, okay, they are not accepting. Yeah, so you can either use thin layer chromatography and electrophoresis, or paper chromatography and electrophoresis. Okay, don't simply give answer mass spectrometry and so on. No. Okay, this one you need to analyze analytical technique. Okay, so you need to separate the amino acids first. Okay, once you separate, okay, how do you separate? Electrophoresis. Then you need to put separate them. Okay, so you need to also use the thin layer chromatography, or you can use paper chromatography. It's fine. Okay, 1 mark. Now, number 7. Number 7, define the term electron affinity. Now, electron affinity is not just ability. Please remember this. It's not ability. Okay, I think students get confused with electronegativity. Electronegativity is ability, okay, of any element to attract the covalently bonded electron to itself. Okay, but electron affinity is different. Electron affinity is not ability. It is the energy change. Okay, it's the energy change when one electron is added to each atom or ion in 1 mole of gaseous atom or ions. Okay, so please remember this. This is the definition. One electron is added to each atom or ion in 1 mole of gaseous atom or ions. Define the term lattice energy. Okay, this is also very popular when you want to define. Energy change when 1 mole of ionic compound is formed from the gaseous phase or gaseous ions. Okay, that's going to be 2 marks. Okay, so the 2 marks is coming from, okay, it's coming from the energy change, okay, when 1 mole of ionic compound is formed. Okay, so that's going to be 1 mark. Another 1 mark is to tell that it is going to be in gaseous phase ion or gaseous ion. So if anything missing here, okay, you will not get the mark. Now use the following data and relevant data I have calculated for you, okay, to calculate a value of enthalpy change of formation. Now, if you want to calculate the enthalpy change of formation, first thing is to write the formation equation. So I wrote the formation equation. Zinc Br2 solid. So if I want from, it must be formed from zinc. Formation means you form from its standard condition. So zinc is always in solid form. Br2 is in liquid form. So it must be something like this. Then I need to think, or do I have formation data or other data that I can use? In this case, I don't have formation data. So I need to use the longer method, which is going to be the Born-Haber cycle method. So I need to construct the Born-Haber cycle method, and they didn't tell you to construct. Okay, but okay, here you see you need to construct an energy cycle. Okay, so it is some sort of a hint for you already. Okay, but okay, even though it's 4 marks, okay, you need to show them your working. So the working, how do I show? Okay, so I start from here, zinc in solid form and then Br2 in liquid form. I start from here. Now, what I need to do, okay, first I change them into zinc in form of gas. That is going to be enthalpy change of atomization. Okay, so that is going to be 131. I put 131. Then after that, I need to change the Br2 liquid to gas. Okay, so this one is going to be vaporization. So you just put 31. So it changed into gas. Now, next step, okay, is to change, okay, zinc is already in gaseous form, 1 atom already. But the Br, okay, there is no atomization data. You can see there's no atomization data. Okay, so I still need to change it into Br, atom, 2 atoms of Br. So how do I do that? I go and look at my data booklet, find out the bond energy between Br and Br. And you will find out that in the data booklet, it is written as positive 193. Okay, positive 193. If you want to break the bond between Br and Br, okay, it's there. So you need to look for, okay, the mode. I think the one that you need to look is, let me show you. Yeah, the one that you need to look is the bond between Br and Br, not at the polyatomic. So here you look from, okay, this is polyatomic. Don't look from here. Okay, polyatomic means you have multiple atoms. Okay, so you always look at diatomic molecules because Br is going to be a diatomic molecule. Okay, so Br and Br, you look at here, 193. Okay, quite simple. Okay, you just look over there. Once you have that, okay, we just continue. Okay, just put the 193 there. Do I need to times by 2? The answer is no, because Br and Br, when you break, you are going to get 2 Br. So it's 193 is enough. Okay, no need to times 2. After that, okay, you need to change into zinc 2 plus. How do I have zinc 2 plus? You need to have first ionization energy and second ionization energy. So this is the data I got from the, I received from the data booklet. So 908, and then the second ionization energy for zinc is going to be 1730. So I put it over there. The The next part is the Br will join with the 2 electron to give you the 2 Br minus. This is what we call electron affinity. And electron affinity is going to be negative. So from here, they drop. Okay, so I just put 2 times 325. And the last one is going to be zinc gas and then Br minus gas. This one is what we call as lattice energy. Okay, the energy required to form bonds for them to be in lattice. Okay, for them to form the solid NaBr2. Okay, so the solid zinc bromide, zinc bromide. So once we have that, okay, I calculate. I will notice when I add these two numbers, I get 3328. When I add these entire numbers, I see 2993. It means that this zinc Br2 solid must be lower a bit, okay, than this line. Okay, why? The distance, you can see the distance. When it is lower, it is just telling me automatically this is going to be a negative value. It's going down. So when it's going down, so we need to calculate this. Quite easy to calculate. 3328 minus 2993. And at the end, because it's going down, you need to give me the value in negative. When I do that, yep. Any question? Okay, when I do that, I will get the negative 335. If you want to show using the clockwise equals to anti-clockwise also can. Okay, please go ahead. Okay, please go ahead. If you are using this method also, make sure, okay, my advice is, if you want the total 4 marks, okay, don't waste any of the marks. So I will strongly suggest to write down 131 plus 31 plus 193 plus 908 plus 1730. All these are clockwise. So plus 2 times negative 325. Okay, plus all these clockwise. So plus negative 2678. This is anti-clockwise equals to enthalpy of formation. So you calculate, you are going to get enthalpy of formation is going to be negative 335. Okay, so if let's say the examiner wants this method of working, so you can also write it down, no problem. Now the lattice energies of these three compounds, they are shown, and they say explain why there is a difference between lattice energies of zinc bromide and zinc chloride. Okay, the difference over here is we know that the zinc chloride is going to be lattice energy is more, okay, compared to zinc bromide. So why zinc chloride has more lattice energy? Okay, the answer is quite simple. The only thing that is changing is not the cation. The only thing that is changing is going to be the anion. And this anion, Cl minus and Br minus, okay, Cl minus, okay, is going to be smaller, okay, Br is going to be bigger. So if you have bigger ion, okay, the bond between, or the bond energy between, ability to form bonds between zinc 2 plus and the Br will be weaker, okay, because they are bigger. Okay, Br is bigger. So here, okay, what is going to, why there is a difference between that? One, your answer, you need to mention about, okay, the size. Okay, so I wrote it over here. Br is going to be a larger ion. So 1. And then, okay, the lattice energy, therefore, okay, will be lower, okay, than zinc chloride. Sorry, it's lower than zinc chloride. Okay, therefore we can just say that the attraction, okay, between the zinc 2 plus and Br minus is going to be less. Okay, so you explain about that. It's 1 mark. Explain why there is a difference between these two then. Okay, now this is going to be zinc 2 plus is going to be the same. Okay, but you see here Cl and O. Cl is Cl minus, O is 2 minus. The charge is more. How about the size? when we look at the size for oxygen, okay, in comparison to Cl, oxygen is smaller, okay, smaller ionic radius. So here I will say for zinc oxide, okay, the O2 minus is small and has higher charge. Okay, because they are small and having higher charge, it means the ability to bond, okay, ability to bond with zinc, okay, is more. So if there is going to be more ability, okay, therefore the lattice energy will become bigger. Okay, bigger when in what sense? Which one will be bigger, zinc chloride or zinc oxide? The one lattice energy is more for zinc oxide. Okay, because one, okay, smaller uh, O2 minus, smaller ion, and at the same time they have more charge. Okay, so ability to bond is more, lattice energy is more, zinc oxide. Please mention about, okay, please mention about this small and higher charge. That will give you another one more mark. Okay, now next question, number 8, the last question. Define the term standard cell potential. Now standard cell potential is going to be the potential difference between two half cell or two electrodes in a cell. Okay, so different potential difference between two cells, okay, two half cell under standard condition. If you just say standard condition is not enough, you need to mention that it is going to be at 1 atmospheric pressure, 298 Kelvin, and all the solutions are in 1 mole per dm cube. So you need to mention all this. If not, you will get only 1 mark. Now, an electrochemical cell is going to be set up to measure the standard electrode potential. This is going to be, you go and look at your my PowerPoint and your textbook. These are going to be, both also are aqueous. Okay, the electrode is also aqueous. Okay, the electrolyte is also going to be aqueous. And then you have, this is going to be the gas, okay, gas method, okay, the Cl2, and then you have Cl minus. So complete the table with the substance used to make the electrode. Now for this one, okay, this is going to be for this CO3 plus and CO2 2 plus, the electrode that are suitable for this is going to be platinum. Okay, you want something that can able to conduct electricity better. And then for the Cl2 and Cl minus, okay, always remember, if we want to measure the E cell related to anything that is involving gas, it must be using platinum, because they are not they are able to be resistant, okay, to corrosion. Okay, so they do not, they are also inert. Okay, they don't react, so we use them. Okay, the only potential downside of this is going to be it's expensive. That's it. Okay, now use the data in the data booklet to calculate the E cell. This is very important. Okay, you have this. Okay, using this, I'll construct the standard reduction potential. So I construct the standard reduction potential, standard reduction potential. This is very important. You look at your periodic, your data booklet, and you look for the number. Okay, I will notice that for this number is 182, and 1.82. Okay, 1.82, and for this I'm going to get 1.36. Okay, so next thing that I need to do is to identify which one is more bigger. I notice the first equation is more bigger. It will move to the front, and this one is will move to the left. Okay, because of the 1.36 and 1.82. Now, once you have that, it means if I want to calculate the E cell, it's supposed to be 1.82 plus, okay, this is going to go to the left, so it's going to be negative 1.36. So when I do this calculation, I will get 0.46, and this is going to be plus. Okay, please remember this. So it's going to be 0.46, okay, volt. Write an equation for the overall reaction. Okay, quite simple also. CO3 plus electron, okay, to become CO2 plus. And this one is going to the left, okay, so it's Cl minus. It's going to give you Cl2 plus two electrons. So I need to eliminate the electron. Okay, so what I need to do, I put 2, I add electron, and electron will be gone. Okay, so I will have 2 CO3 plus. Okay, let me share the screen again. So we only use platinum for metal, metal ion, and gases. When do we use metal electrode? Now, for this one, okay, to answer this question, Justin, platinum, okay, we use for uh, uh, for the metal and metal ion, okay, we use, you check over here, metal and metal ion, if I'm not mistaken, we use the metal. I think for the ion and for ion and gas, we use the platinum. Okay, let me actually share the screen for the electrochemistry part. Okay, this is what we learned last time. Hold on, yeah. Okay, so metal, metal ion, non-metal and non-metal ion, ion and ion. Okay, so if you are using, you see, Justin, this is what I mean over here. If you are using metal and metal ion, okay, so you are using the electrode, we are using the copper, the metal itself, okay, the metal itself. But if we are using the non-metal and non-metal, for example, if we are using gas and gas, okay, hydrogen gas and Cl2, so both also we use platinum. And if you are using ion and ion, for example, Fe3 plus and Fe2 plus, you cannot use iron, okay, as your electrode. It must be platinum. Okay, it must be platinum. So I hope you understand this one. Okay, so so we use platinum for metal and metal ion and gases. The response is no. We only use platinum for metal ion, and non-metal, which is gases. Okay, when do we use metal electrode? When it is going to be metal and metal ion. Okay, Justin? Okay. So let me move on. Okay. So here, where did I stop? Okay. So platinum and platinum, yeah, this one is done. Okay, this is done. And okay, this is done. I don't know which one I did until, I think I've done until this. Okay, platinum and platinum. And then when you have this, you learn how to calculate. Okay, and then we want to include all of them. So the 2 electron and 2 electron you cancel. Okay, so I want the electron to be gone. So I will have 2CO3 plus Cl minus. You are going to get 2CO. Sorry, it's going to be cobalt. Cobalt 2 plus Cl2. So this one must be 2. Okay, I think that's it. Okay, this is going to be the equation for the overall reaction. Okay, so if you want to write aqueous, okay, aqueous, and this is going to be gas, go ahead. Yeah. Now, a fuel is an electrochemical cell, okay, that can be used, okay, to uh, generate electrical energy. So you have this methanol oxygen fuel cell, blah blah blah. They have given you this, okay, but I think the question what they want to ask you is to calculate the volume of CO2. This is very important, the beginning part of the calculation. Okay, so here when you want to calculate the volume of CO2, you need to look over here, 6 electron. Okay, if you have 6 electron, it means that 6 Faraday is required to form 1 mole of CO2. You look at this. Okay, we are looking for the CO2. So 6 Faraday is going to be for 1 mole. So first we find the Q equals to IT. Okay, so current is 2.5. Okay, the T must be in second, 30 times 60. Okay, you can calculate also. I'll calculate for you. Okay, so 2.5, 30 times 60. So 4,500 joule. Okay, so when you have this, okay, when you have this is going to be the joules that you have. So 1 Faraday, okay, you need to memorize this 96500, yeah. So what 1 Faraday is going to be 96,500. Okay, you can refer to your data booklet. Okay, so sorry, this is, I think it's column, yeah, column. Okay, so this one is going to be how many columns? Okay, it's going to give you 1 mole of CO2. So when I calculate this, 6 times 96500, I'm going to get 579,000 column for 1 mole of CO2. I want for 4,500 only. So 1 column, 1 divided by 579,000 mole of CO2. So I want 4,500. So 4,500 column is 4,500. You times this. Okay, so 579,000 mole of CO2. Okay, 4,500. You will get 7.772 times 10 negative 3 mole of CO2. I want volume, okay, and I know that 1 mole of CO2, okay, they will occupy 24 dm cube of volume. Okay, so just times, okay, I will get how many dm cube. Okay, just times 24 times 7.77, so times 24, I will get 0.1865, okay, dm cube. I want in cm cube times 1000. So when you times 1000, 186.5. I think better 3 significant figures. So we just change it into 187 cm cube. Okay, that's it. Okay, for this paper.